Welcome to Module 7, Molecular Bonding and Chemical Equilibrium. This video provides a comprehensive exploration of molecular interactions and dynamic chemical systems, focusing on both chemical bonding and dynamic equilibrium. We will cover four main sections. First, the fundamentals of chemical bonding, exploring the forces that define molecular architecture. Then, we will examine molecular geometry and how it relates to macroscopic properties. The third section focuses on chemical equilibrium principles, where dynamic systems achieve a balance between forward and reverse reactions. Finally, we will look at applications and future directions of these concepts in our world. There are three primary types of chemical bonds. Ionic bonds involve electron transfer between metals and nonmetals. Covalent bonds involve electron sharing, and metallic bonds feature a delocalized electron C. The bonding continuum is determined by electronegativity differences. This ranges from pure covalent to ionic bonding. Molecular polarity is quantified by the dipole moment, which is the vector sum of bond dipoles, and influences solubility and biological function. Next, we explore molecular geometry and properties, focusing on the relationship between three-dimensional molecular architecture and macroscopic properties. VSEPR theory helps predict molecular shapes and bond angles by minimizing electron pair repulsion. Lone pairs occupy more space than bonding pairs, leading to compressed bond angles, which defines geometries like linear, tetrahedral, and bent. Bonding type dictates bulk physical properties. Ionic compounds have high melting points and conduct electricity when molten. Metals are conductive and malleable due to the electron C. Covalent molecules generally have lower melting points and are non-conductive. Our third section covers chemical equilibrium principles. This explores dynamic systems where the rates of forward and reverse reactions are balanced. Dynamic equilibrium is reached when forward and reverse reaction rates are equal. The equilibrium constant, Keq, quantifies this balance. A large Keq favors products, while a small Keq favors reactants. Keq is constant only at a fixed temperature. Le Chatelier's principle states that a system at equilibrium will shift to counteract any disturbance. Changes in concentration, pressure, or temperature affect the position of equilibrium. For example, removing a product drives the reaction forward. Equilibrium principles are vital in living systems, such as blood pH regulation and oxygen transport. Industrially, processes like the Haber and contact processes are optimized using these principles to maximize product yield efficiently. We have now completed Module 7, Mastering Molecular Behavior from Bond Types to Equilibrium Applications. The next step is Module 8, where we will explore acids, bases, and redox reactions.